So our next lesson in chapter 9 is actually a whole bunch of shortcuts. In fact, the next couple lessons are going to be a whole bunch of shortcuts that will save us some time, big time. And our shortcuts today are going to deal with the Pythagorean theorem that we learned yesterday. So the more and more that you do the Pythagorean theorem, you will notice that there are some problems that become familiar because you keep doing the same numbers over and over, and you find like, hey, I know that these numbers always work in the Pythagorean theorem, and those numbers are called Pythagorean triples. So Pythagorean triples are just any set of three numbers that make the Pythagorean theorem work. So if you think of, if I just pick the three numbers that work, a squared plus b squared equals c squared, there are an infinite number of Pythagorean triples, right? If you pick any two numbers, I'll find you a third number that will work. It might not be a whole number, it might be a radical, but it would work, right? So there are an infinite number of Pythagorean triples. However, there are four that we see so often. We see them so often in problems that we're doing this year. You're going to see them so often in things that you do in the future. If you look back and look at the problems that we did last year in algebra, it is these four Pythagorean triples more often than anything else. But also you see them a lot in nature and other places where you wouldn't really expect them. So there are four Pythagorean triples that we're going to want you to memorize. And I'm going to show you how awesome it is that if you do memorize these, how much time it will save you. So maybe there is one that jumps out at you right away, and I'm wondering if it isn't 3, 4, and 5. So that is our first Pythagorean triple, 3, 4, 5. 3 squared plus 4 squared equals 5 squared, right? 9 plus 16 equals 25. So the Pythagorean triple of 3, 4, 5. This is the most often used Pythagorean triple. Now, the biggest question I usually get is people say, okay, well, the next Pythagorean triple would be 6, 8, 10. But the thing is, that is not a new triple. That is the 3, 4, 5 triple, but it's just a multiple, right? So if 3, 4, 5 works, then multiplying everything by 2 will work, and multiplying everything by 3 will work, and multiplying everything by 5 will work, right? So when we talk about a triple, we're talking about the basic, the most reduced form of it, and all multiples included. Multiples included, right? So if you see 6, 8, and 10, that's the 3, 4, 5 triple. It's just multiplied. And I'll show you how to do that in a little bit, but I just want you to know that. So when we do these four different Pythagorean triples, and it includes all of their multiples as well. So 3, 4, 5 is the first one. The second one is 8, 15, 17. That's a very, very common one. The next third one is 7, 24, 25. And our last one is 5, 12, 13. So those four, not really in that order, although I will say 3, 4, 5 is the absolute most common. But 8, 15, 17, 7, 24, 25, and 5, 12, 13, all very commonly used as well. So those four you need to memorize. Now there is one more that you possibly could, and that additional one is 9, 40, 41, but that one isn't used very often, and if you don't remember that one, that's okay. But you definitely need to remember 3, 4, 5, 8, 15, 17, 7, 24, 25, and 5, 12, 13. They may seem kind of random, but the more you use them, they're going to get ingrained in your head, and you just need to know those by heart. So start working on memorizing those four. Now, let's talk about how do we use Pythagorean triples. So let's go to those problems that we talked about before that said, is it a right triangle? Remember last lesson where we talked about the converse and we had to do the Pythagorean theorem to see if it worked? Well, we could do that here, right? We could say, okay, this side is the longest side, so that would have to be C. So I could say 15 squared plus 36 squared equals 39 squared. And I know 15 squared, but yuck, I'd have to use my calculator. Those are going to get huge, right? So instead of doing that, what I can do is I can look for a triple. Here's how I'm going to look. 15, 36, 39. Do they have a common factor? Well, 15 is 3 times 5. 36 is 3 times 12. 39 is 3 times 13. Now notice I wrote them all by multiplying and not dividing. And I really, really, really want you to do that. I don't want you to write divided by 3, like 15 divided by 3 equals 5. Don't do that, and I'm going to show you why in a little bit. It may not really make a huge difference on this problem, but coming up, I promise you it will. So please write it as multiplying. Don't write it as dividing, okay? So 3 times 5, 3 times 12, 3 times 13, 5, 12, 13. That's a triple, right? 5, 12, 13, that's my triple right there. So this has to be a right triangle, because if it's a Pythagorean triple, then it's got to work, right? A squared plus b squared will definitely equal c squared. So if you see that it is a triple, by showing your work just like this, all you have to do is say Pythagorean triple, 5, 12, 13. And we'd answer the question, yes, right? This is a right triangle. So the work that you need to show is showing what your sides are multiplying, right? So showing where that comes from, and then writing Pythagorean triple, 5, 12, 13. So you have to write this and you have to write this, but that's a heck of a lot less work than writing out all of your Pythagorean theorem and getting your calculator out and doing every step, right? Huge, huge shortcut. All right, so let's look down at the bottom here. 14, 48, and 50. See if you can find a Pythagorean triple in there. Let's see. 14 is 2 times 7. 48 is 2 times 24. 50 is 2 times 25. That would be 7, 24, 25. There's our triple. So we write Pythagorean triple, 7, 24, 25. And we answer the question, yes, this is a right triangle. Awesome. Okay, let's look at our last one here. 24, 42, and 51. Let's see. 24 is 8 times 3. 42 is 14 times 3. 51 is 17 times 3. 8, 14, 17. 8, 14, 17. That's not it. It's supposed to be 8, 15, 17. So this is not a triple. Now, does that mean that it's not a right triangle? Not necessarily, right? Remember, these are only 4 of the infinite number of Pythagorean triples that are out there. Pythagorean triples don't have to be whole numbers, right? So that doesn't necessarily, just because it's not one of our triples, doesn't mean that it's not a right triangle. So we still would want to check it. Now you could argue like, well, if we know the triple is 8, 15, 17, then there's no way that 8 squared plus 14 squared is going to equal 17 squared. So you could say, you could write an explanation. No, it's not a Pythagorean triple. It's supposed to be 8, 15, 17 instead of 8, 14, 17, right? And since there's only one number that's different, it means it's probably not a right triangle. Or you could show your work, right? Now, the cool thing about using this idea of looking for a Pythagorean triple is we don't have to use the huge numbers, 24, 42, and 51. We can use these smaller numbers, because I know that if 8 squared plus 14 squared equals 17 squared either works or doesn't, multiplying it by 2 isn't going to change anything, right? So I could then say 64 plus 196 equals 289. Oh, 260 does not equal 289. So the answer is no. But that was a heck of a lot easier than using those big, big, big numbers, right? So this process that we just did, where we're looking for the Pythagorean triple, even if it's not a Pythagorean triple, and then using the smaller numbers with our Pythagorean theorem, that process is called reducing the triangle. Now, it's not a big deal if you know what the name of that process is, but the fact of doing it is going to save you time, even if it's not a triple. So triples are awesome, right? Way less work. And even if it's not a triple, it's going to save you some time and work in the long run. So what if we just have these triangles like this where we actually have to solve for a missing side and not do the converse? Same idea, right? So let's see. I'm trying to solve for x in number 1. That is the side across from the right angle. So this is C, right? So if I think about, okay, 24 and 45. 24 is 8 times 3. 45 is 15 times 3. Wait, 8, 15. That sounds like a triple, right? That's the start of a triple. So I can use my Pythagorean triples in order to shorten up this process, right? 8, 15, the Pythagorean triple would be 8, 15, 17. So I'm going to use this 17, right? So that means this side would be 17, but it's not 17, it's 17 times 3, right? So be careful. This is why I wanted you to write it with multiplying instead of dividing, because if you wrote 24 divided by 3 equals 8, 45 divided by 3 equals 15, what are you going to want to do with that 17? You're going to want to divide it, right? Because that's what pattern your brain has set up. So the fact that we're writing it as multiplying, 8 times 3, 15 times 3, x equals 17 times 3. And your brain is already in that pattern, so we're not fighting against it to get the right answer, right? So x equals 51, and that is way less work than writing out the whole Pythagorean theorem. This is the work you would need to show. You got to show what you're multiplying each of those sides, right? The factors. You got to write down Pythagorean triple, and you have to write down which triple it is. Don't just write 8, 15, 17. That's just a jumble of numbers unless you write Pythagorean triple with it, okay? So that's the work you need to show. Now, do you think it's really easy to write the answer as 17 instead of remember to do 17 times 3? Yeah, that's the most common mistake. But like I said, the more habits you can get into, like writing all those other sides as times 3, the more it's going to jump out at you and the more often you're going to catch it. But double check those things, right? That's where you're going to find your little mistakes. So that's the cool thing about Pythagorean triples and just that amount of work. Let's look at the bottom one down here. I have sides of 55, 77, and I'm finding that missing side of x. So that's C, right? 55. 5 times 11, 77, 7 times 11. 5 and 7, that's not one of my triples. I have 5, 12, 13. I have 7, 24, 25, but no 5 and 7 together. But again, we can use that idea of the reduced triangle, right? I can use the 5 and the 7 instead of the 55 and the 77 in order to solve this. Now, we just have to be careful, right? So when I say this, okay, 55 is 5 times 11, 77 is 7 times 11. So what I'm trying to find here is going to be y times 11. Now, I would be careful, and I would make sure I would give this a different variable again so that you don't forget to multiply by 11 when you're done, right? So it will be 5 squared plus 7 squared equals y squared, right? So 5 squared is 25, 7 squared is 49, equals y squared. 25 plus 49 is 74. And then I square root both sides. 74. I don't think I can break down 74, right? 37 times 2, 37 is prime, 2 is prime. So this is y becomes the square root of 74. Again, we could say plus or minus radical 74, but this is a side length, so negative doesn't make sense. So y is radical 74, so that means x equals 11 radical 74, right? I have to multiply it by 11. Way easier, way easier. Can you imagine if I had 55 squared plus 77 squared and whatever that was, and I had to try and reduce that radical? Yikes. So do that, reduce your triangle. It will save you time. Even when it's not a Pythagorean triple, right? Awesome. All right. Oh, look at this last one. I want to see how fast you can do it. 3, 4x. Ready? Go. Do you have it? I hope not. Be careful. Notice which side is missing, right? This is not the Pythagorean triple 3, 4, 5. Why is it not the Pythagorean triple 3, 4, 5? Because the longest side in this triangle is 4, and the longest side in the Pythagorean triple has to be 5. 5 has to be the hypotenuse. You cannot have a leg of 5 and a hypotenuse of 4 in the same triangle. The hypotenuse has to be the longest side. So this is not the Pythagorean triple. So instead, you actually have to do the Pythagorean theorem. Luckily, these numbers are small enough. 3 squared plus x squared equals 4 squared, right? 4 is c. 9 plus x squared equals 16. Subtracting 9 from both sides, x squared equals 7. So my answer here, x equals radical 7. So square root of 7. Be careful though. I wanted you to see all 3 of these when you're using those Pythagorean triples to solve for missing side lengths. It's awesome when it's a triple and it works. Look at that first one, right? Super short amount of work. Even if it's not a Pythagorean triple down at the bottom, that idea of hunting for one will save you time and energy in the long run. Don't forget to multiply at the end. And the last one though, be careful. When you're looking for those triples, make sure that your longest side is the hypotenuse. Otherwise, it's not a triple. All right, you guys got this.